Start like with everyone else, just to thank all the organizers, both for the conference and the program that preceded it. I think I've been here for almost 2 weeks now. I've had a great time. I think I've learned a lot, met some new people, everything that's supposed to happen at one of these programs. So thank you to all of the organizers. Okay, so as Klaus said, the title of this talk, Harnessing Dissipation for Spin Squeezing in Metrology. Yes, it's another spin squeezing talk. What I'm going to tell you, I think, connects spiritually to what Peter told us about, what Anna Maria told us about. We want to make our qubits or spins interact in interesting ways that are hopefully useful for metrology, hopefully compatible with experiments. The thing that'll be different in the story that I tell you is we want to make use of dissipative interactions. We want our spins to talk to some kind of common engineered reservoir that makes them interact in useful ways that, again, we can harness as a resource for metrology. So I'll both tell you ideas for how you can use this paradigm to generate highly entangled spin squeeze states, even in a way that reaches the Heisenberg limit. And then I'll tell you about something that, in a way, mirrors what Peter told us about, this idea of encoding and then decoding in kind of an optimal way. I'll tell you a way of doing that with purely dissipative processes. Okay, and I'll use a language that is maybe less fancy sounding. I'm going to describe this as a kind of dissipative spin amplifier. Okay, and I would be remiss if I didn't start by telling you who actually did the work. So this is a line of work in my group that's going to be going on for 2 or 3 years. The recent work has really been led by a postdoc in my group, Martin Koppenhofer, and then previous works involved 2 former postdocs, Peter Grozowski and Kiro Lau. And all of this work has really been inspired from an ongoing collaboration we have with Anya Blazinski JH's group here at UCSB. She's very interested down the line of maybe using these ideas of spin squeezing quantum metrology in a solid state system. So spoiler result, I will not have any beautiful experimental results to tell you about. Solid state is hard. But I'll tell you a little bit at the end how we think these ideas are compatible with her platform. Okay, introduction to spin squeezing. I hopefully don't have to tell you much about that. What's the context? We have a collection of 2-level systems. We're trying to estimate some parameter that we'll acquire in a Ramsey sequence. It'll be encoded in the collective polarization of our spin ensemble as a rotation. What's the basic idea of spin squeezing? Well, quantum noise in the state of that ensemble creates fuzz in the direction that arrow is pointing that makes it difficult to resolve a small rotation. The basic idea of spin squeezing is reduce the fluctuations in the expected direction of that rotation. Okay, and if you can do that, it's easier to resolve that small rotation angle. In principle, you can go from an estimation error that scales as 1 over square root of n, the standard quantum limit, to something like 1 over n, something close to the true Heisenberg quantum limit. So these spin squeeze states, these states that have reduced fluctuations in a transverse spin component, these are entangled states. So the most natural way to generate an entangled state is to make your spins interact. So I already heard about this collective one-axis twist Hamiltonian and all-to-all Ising interaction. This is a very powerful route for spin squeezing. If you get more sort of adventurous, you could try for this 2-axis twist, Hamiltonian. That gives you even possibly Heisenberg limited squeezing. We heard about other kinds of Hamiltonians with not fully collective interactions in Anna Maria's talk. In this talk, the idea is different. What if we just get rid of the Hamiltonians and we construct some sort of dissipative interaction that does the squeezing for us? So often, how do we generate these collective spin-spin interactions? We have our spins interact in a detuned way with a cavity with some resonant mode. Maybe I can interact resonantly with the dissipative cavity mode and play some tricks such that dissipation will actually generate the spin squeezing I want. So how do I do that? Are there advantages? Could I do this in a real experiment? Okay, the other problem I'm going to focus on a lot here is one I don't think we've heard about, and one that is crucial for possible solid state applications. Is spin squeezing of any use at all if you have a terrible final readout? Okay, and so we have our beautiful, possibly spin squeeze state. There's information on the parameter in the average value of, let's say, the y component of this collective spin. Here's my estimation error. Here is the fundamental noise of that quantum state. Maybe this has been spin squeezed. But in general, if I have imperfect readout, there's going to be some junk added to that. So I'm going to refer to that as readout noise throughout this talk. I'm measuring it in units of the projection noise of a spin coherent state. In the examples I'll consider about this, readout noise will really scale with the number of spins n in the system. So at first glance, if this term, if this C is much, much bigger than 1, there's no point worrying about the projection noise because it's just not the dominant thing. Okay, so we have many experts in the room, and many experts know, aha, there are clever tricks that let you get around this, right? Sometimes these go under the idea of interaction-based readout. Maybe the most famous version of this, which I'll tell you more about, is the so-called twist-untwist scheme, where you use that one-axis twist Hamiltonian twice in a very clever way. So there are ways of trying to make use of spin squeezing, even if this is an issue. Okay, and what I'm going to try to tell you about, well, there are these nice Hamiltonian approaches based on unitary evolution. Could there be a dissipative version of those schemes, right? Could I play some dissipative tricks twice in such a way that I can take advantage of squeezing and not be limited by that imperfect readout? Okay, and so the talk is short, and I don't want to talk about depressing things, but I need to show this slide once. The application we have in mind eventually is trying to play with some of these ideas in a solid state system. So NV centers or other defects in diamond. Okay, long story made short, these defects in diamond basically give you a controllable two-level system that you could use for sensing, and people do use it, right, with great success for magnetometry, sensing temperature, electric fields. The readout is based on spin-dependent fluorescence. By some standards, it's very good. By other standards, it's not very good at all. So this is the fluorescence for the two different qubit states of interest. The contrast is not very good. The difference disappears on a very short time scale. You have problems with collection efficiency. So if you take what I think is one of the best results for a large spin ensemble, this extra readout noise in units of the projection noise, it's a factor of 70 bigger. Okay, and most experiments are much, much worse than that. Okay, so at first glance, like, look, we have a big problem. Forget about spin squeezing. How do I even reach the standard quantum limit? Okay, and so what is this talk going to be? Well, the first thing is, given this experimental reality, let's just forget about spin squeezing, right? We've got a bigger problem to deal with. Let's forget about spin squeezing. Let's just ask, given that this thing here is like 70 squared, is there some way I could actually approach the quantum limit, the standard quantum limit? Okay, and the idea is very simple. Let's build a spin amplifier. Okay, so this is the dream of what we'd like to achieve. Here is our estimation error, right? This is the sensitivity of SY to the rotation I'm interested in. This is the fundamental projection noise. This is that unwanted added noise of the final readout. So what's the idea of a spin amplifier? Well, SY, that small component of the spin, right, that has information, I'm just going to make it bigger. So the dream would be to have some kind of gain of this amplifier. Everywhere you see an SY in that equation is going to come with a factor of G. So if I could achieve this, right, this term here doesn't change at all because I'm going to amplify the fundamental noise and the signal the same amount. This term that's associated with the added noise, there's only a G squared in the denominator. Okay, so if I could do this, this would be beautiful. I could just reduce that unwanted added detection noise, right, by some factor, G squared, that is hopefully large. Okay, so that's the dream. The question is, can you really do this without other things going wrong? The biggest thing going wrong is, are you sure you don't corrupt the quantum state in this process? And to use amplifier language, we could say, what is the added noise of this amplification process? There's normally no free lunches, right, in any kind of quantum measurement problem. There's the same question here. Okay, so if we can solve this problem, and I'll try to tell you that we can, then we can be more ambitious. Okay, if I've got a trick for dealing with that detection noise, when I just start with the product state, what if I start with a spin squeeze state? Can I still make use of that despite this enormous detection noise in some kind of dissipative way? Okay, and so I'll tell you again, as I promised, some dissipative version of twist-untwist, these encoding, decoding protocols. And the basic idea, in both of these things I want to tell you about is to basically exploit the physics of superradiant decay. Okay, and I'll tell you how to engineer that superradiant decay. And in this case, we're going to do something a little bit fancier. We're going to engineer something that looks like squeezed superradiant decay. Okay, that might sound scary from an experimental point of view. I'll try to sketch ways you could actually implement this in real experiments. Okay, so the first example, and again, the time is short, so I'm going to reduce it to almost just one slide. We're starting with a product state, right? No spin squeezing. We have this enormous amount of detection noise. We want to get some amplification. So I imagine my spins are interacting with some lossy cavity mode, right? Resonantly. I imagine eliminating that cavity mode. What do I get in ignoring other things that could go wrong? I generate some collective decay of the spin ensemble. So this is a Lindblad master equation. There's one decay operator that's the collective S minus, describing all of the spins. Okay, so this is superradiant decay. Huge history studying this in quantum optics. You normally focus on the outgoing photons as being interesting in superradiant decay, the burst, what is the properties of that radiation. Here we're going to focus on what actually happens to the spins. Okay, so imagine I've acquired this phase, this rotation of interest. I rotate that state up to close to the North Pole. Okay, so again, the information is still in SY, but now SZ is almost its maximum value of n over 2. So what happens under this dynamics? Not much interesting. The spin will eventually just decay to the South Pole, right? But this is a collective decay process. Total angular momentum is conserved. What's the trajectory it will take? And this is a little bit exaggerated. It will follow a trajectory that when it crosses the equator, it will have a value of SY that remembers the initial value of SY. But now that value of SY is going to be bigger, right? So the idea is SY as a function of time will be an amplified version of what it started with, right? And that gain factor here can be as large as square root of n, where n is the number of spins. So really, really simple idea. It's just this process is, the decay process is constrained. Here's the mean field equation of motion that gives you this kind of, time-dependent growth rate. That's the physics we want to exploit. Okay, and so a little bit more details. What is this gain as a function of time? This is for 120 spins. You see that there's this sharp peak, which is basically when the spin ensemble is crossing the equator, where you get this nice value of gain, and up to a factor of a half, it really scales as the square root of n. This is what this plot here is showing. So we've seen this in mean field theory, doing exact numerics. That's all fine. So we have gain, right? That was part of the story, and the gain could be very large, right? We need some way of being able to shut off the superradiant decay at the right point, but for different experimental platforms, there are ways of doing this. The thing I have, and again, this is what the experimental protocol would actually look like. So you have the normal steps in your Ramsey sequence, right? Prepare a superposition, acquire phase, eventually move the information to the z-axis. In between, you insert these two steps for the superradiant decay. Move the spin close to the North Pole, turn on this decay for just the right amount of time. So what's the elephant in the room? There's no free lunch. If I'm amplifying with large gain, there must be some added noise in the problem. Okay, and so imagine we just think about a bosonic problem, which is something I'm much more familiar with, and it's much easier to describe. Here is a very simple input-output relation for a bosonic amplifier. A is just some photonic lowering operator. And so what Carl Caves and others taught us is, if you have a relationship like this between the input operator and the output operator, and G is really large, there's got to be something else on the right-hand side. There has to be added noise, otherwise you violate commutation relations. And this added noise has to be at least as big as the vacuum noise, okay, for a kind of amplifier that is not phase sensitive. Okay, so if I go back to my formula for my estimation error, right, including this kind of gain that I'm generating, right? So again, I've just scaled everything by g. I reduced the detection noise by a factor of g squared. This is just the initial noise in my state. But now, whatever excess noise there is in that state, I'm going to call that the added noise of this spin amplifier. And again, measured in units of the spin projection noise of a coherent state. That's like the vacuum noise. Okay, and so the kind of amazing thing that we found, or I find it kind of amazing, so if you just took this argument and tried to apply it to the spin case, you'd be, well, maybe the best you can do is this thing sigma squared add is 1, right? The amplifier adds the vacuum noise. And we find that in the large N limit, it really comes very, very close to that. We get this 1.3. Okay, so one interesting open question, is this the quantum limit for a spin amplifier? Can you actually do better, come to 1? You know, I don't have the answer to that. Okay, but the upshot is, and I think that's, this, if we're not worrying about squeezing at all, this is potentially a really powerful way to sort of overcome the problem with detection noise. So this is now showing results for the estimation error in units of the standard quantum limit as a function of the number of spins, taking this best case, like NV ensemble, answer. So if I didn't do any amplification, I'm always a factor of 70 off the SQL. It doesn't matter how many spins I use. In principle, with this amplification trick, the gain is getting bigger and bigger and bigger as I have more and more spins. You can approach the standard quantum limit within a factor of 2. And that factor of 2 is that 1.3 added noise. One other nice thing about this is always this like dream that why do things using dissipation when you could do it with a unitary? Well, maybe if the way you do things is dissipative, it's more robust to bad dissipation. Okay, and this is a case where at least partially that holds true. This is showing what happens to the gain as I add single spin dephasing. I think this is single spin dephasing. And we're measuring that in terms of a collective cooperativity. This is for different numbers of spins. What this is showing is basically to get the maximum possible gain that scales with square root of n, you only need a collective cooperativity that is large. Okay, and so that I would argue is a, not such a crazy requirement in terms of how weak does the single spin decoherence have to be. I can talk more about this if there's time during the questions. If you use amplification generated by a Hamiltonian one-axis twist process, then you actually find to get the maximum gain that also scales like square root of n, it's the single spin cooperativity that shows up on the x-axis. Okay, so if you're in this regime where you're just trying to fight detection noise and you want to get all this gain and you want that gain physics to occur even if there's single spin dissipation, this dissipative process seems to have real advantages in terms of robustness. Okay, so I think the next thing is trying to get even greedier and say, okay, can we actually make use of squeezing in this story? Okay, so now we imagine that you're able to start in some spin squeeze state. You still have a terrible readout. Okay, and now you want to again have some magic process that gives you gain, gets rid of the detection noise. But now you really want to be limited by this noise here that's going to be much, much smaller than the n over 4 we'd associate with the product state. So now I want an amplification process where this added noise, it can't be sigma squared is 1, because then this will dwarf any squeezing there. I need an amplification process where this is actually going to 0. So at the end of the day, all I'm left with is this in the numerator. That is the beautiful low fluctuations of my spin squeeze state. Okay, so how do I do that? And again, I want to do it in a dissipative way. So to figure out, or to at least come up with a process that might do this, how might we do this if we weren't talking about a spin ensemble, but we were just talking about a single bosonic mode? Okay, and what we would do is we would make use of phase-sensitive amplification. We would just try to measure x and not p. And what's a dissipative way of doing that? And so this is just highlighting, we don't want those terms, right? So here's a bosonic way of doing this, a completely legitimate, not violating quantum mechanics, bosonic dynamics. So I'm splitting my photonic lowering operator into sort of two Hermitian quadratures, x and p. If I could generate a dynamics like this, right, where it looks like x and p are both just damped, right, gamma's positive, but the noise associated with that damping is much smaller for x than p. So think of these as just, real white noise, right? So commutation relations are preserved because this is e to the minus r, this is e to the plus r. So if gamma is positive, this dynamics will generate squeezing, right? The x quadrature, right, will just decay exponentially in time. It'll be limited to this e to the minus 2r. If I make r bigger and bigger and bigger, more and more squeezing. Okay, this also generates noiseless amplification. All I have to do is flip the sign of gamma, right? So if I flip the sign of gamma, then I have exponential growth of x, right? X is going to get bigger and bigger and bigger. But again, the noise associated with that anti-damping, that is very, very small if r is large. So in the bosonic case, there's a simple kind of dynamics I could write down that seems to do both the things I want. It gives me a way of generating squeezing. It gives me a way of doing amplification where I don't add noise to the thing that I squeezed. So how do I turn this into something I can do with spins, right? So the first thing to realize is, yeah, I don't like Langevin equations. I can switch and work with a master equation. So what is the master equation that corresponds to this dynamics, the Lindblad master equation, in the two cases where gamma is either positive or negative? And the master equation, so D here is that standard Lindblad superoperator. In the case where I'm trying to do squeezing, right, it corresponds to the jump operator being a linear combination of A and A dagger, where the coefficient of A is bigger than the coefficient of A dagger. Okay, so I think for most people, this looks a bit weirder than this equation here. So we might call this cooling of Bogolyubov mode. If you don't like that, you could ignore it. This is exactly the same as this dynamics here. And in the case where I make gamma negative, and I want to get this amplification physics, it's basically the same master equation, but the role of A and A dagger have been reversed. Okay, so we now have dissipative processes, both for generating squeezing, in this single mode bosonic case, and for generating amplification. And again, there's a variety of experiments that have probed this in one form or another in bosonic systems, in optomechanics, in trapped ions, even in superconducting circuits. Even the idea of using this as a good way of doing readout and amplification was probed in a nice experiment from Konrad Lehnert. So now the idea is, okay, now I know what to do, right? How do I turn this into something that'll work for my spins? I'm just going to turn A's and A daggers to spin lowering and raising operators. And we know that that's not completely valid, because to really get lots of squeezing, we're in a regime where, leading order Holstein-Primakov is not relevant. Spin lowering is not the same as A, but we can hope for the best. Okay, so what is the final protocol we're going to think about? This is this kind of, by now, famous twist-untwist protocol, an example of this kind of encode-decode protocol, where you would first generate squeezing with this one-axis twist Hamiltonian, then write a phase, and then amplify by applying that one-axis twist Hamiltonian with a minus sign. So we want to do something similar, but each of these steps is now going to be represented with the dissipative process. So again, for bosons, I had jump operators that were linear combinations of A and A dagger. Now I'm using linear combinations of S minus and S plus. This is the dissipator that I hope will generate the squeezing. This is the dissipator that I hope will generate the amplification. Okay, and what I'm going to try to convince you is this actually works. Okay, and it's not as simple as these two things being related by time reversal symmetry, but there is a kind of matching of how you're doing the squeezing, how you're doing the amplification. This is a way of being able to use squeezing even if you have a lot of readout noise. It also has some interesting robustness properties over this one-axis twist Hamiltonian. In close 5 minutes? Okay, perfect. Okay, so first the squeezing step. Let's just focus on this. So for the squeezing step, here is our master equation. To the experts in the room, this will be familiar because this was studied way back in the 90s, if not earlier. This is the master equation you would write down if you had a collection of two-level atoms that were driven with squeezed light. Okay, so this master equation in the steady state, right, there's a unique steady state where the spins are highly squeezed. Okay, and so we have a recent work that, studies the dynamics here in great details. There's a couple of surprises that I don't have a huge amount of time to get into. So this is basically showing squeezing measured by the Wineland parameter as a function of this R parameter, so e to the 2r and dB. And you see that, okay, if I look at the solid curve here, for 200 spins, the squeezing gets better and better and better and eventually saturates as R gets very large. And it saturates at pretty much the Heisenberg limit for spin squeezing, so 1/n, so better than one-axis twisting. Super weird thing is, what if I change the number of spins by 1? Well, then there's this magic point where the squeezing goes away, and I have huge fluctuations in that quadrature. Okay, so the good news is there's a way of using this dynamics to get a lot of spin squeezing, right? The kind of interesting thing is there's this really interesting sensitivity to even versus odd that persists no matter how big n actually is. Okay, but for our purposes, the first aspect of the story works. There's a way of generating dissipative spin squeezing. You do not have to shine squeezed light on your atoms, right? Not just our work, but other works. There's a lot of clever tricks where you can kind of fool your spins into thinking that they're interacting with a squeezed reservoir by basically playing clever driving tricks on your cavity. Okay, so there are ideas using Raman processes with 4-level atoms in this paper from Emmanuel Della Torre. We have ideas where you could use optomechanical interactions, superconducting circuits to also generate this effective dissipator. Okay, so we have the squeezing. What about the anti-squeezing? Well, it turns out, what I wrote here was, oh, you now need to generate the dissipator daggered. Turns out life is even easier. All we have to do is keep the same dissipator and then move our spin state up to the North Pole, right? Because if I at the North Pole versus South Pole, what's an A dagger? That notion kind of gets reversed. Okay, so for the amplification part of the story, right, we've prepared the spin squeeze state, we've encoded a phase in it by rotating it, we again move up to the North Pole, and now we just let this thing relax, right? We generate amplification from this master equation dynamics. And the same way as the story without squeezing, when you cross the equator, we hope to get a lot of amplification. So a big factor G that will suppress this detection noise. What's going to be different this time, we really hope that this added noise will be much, much smaller than 1. Because we really want to make use of the fact that, hey, we've squeezed these initial fluctuations in SY. Okay, so again, the protocol kind of looks the same. It's just generating the squeezing happened before this step here. It's done with this dissipator. This decay process that gives us amplification, it's also done with the same dissipator. Okay, and so the issue here is, like, for bosons, I could get as much amplification as I want by making gamma T really large. I could get as much noise suppression as I want in the amplification by making R as large as I want. That's not true for spins, right? The fact that I have this finite dimensional Hilbert space, it's not at all a priori clear that you can do both these things, right? Get lots and lots of gain and still have the nice noise suppression. Okay, long story made short, despite the complexities of the added nonlinearity in the spin system, it still works. Okay, and so here is an example, number of spins, what is your estimation error, right, squared compared to the standard quantum limit. So this is our, green curve here, and these different points here. This is our optimized, SSR super radiant, squeeze super radiant, amplifier. And the gray region here is, at or above the standard quantum limit. So we're doing better than the standard quantum limit. We have single spin cooperativities that are order 1/2, right? But in this plot, if you had the perfect one-axis twist-on-twist protocol, cooperativity infinity, it's doing better. That's this red dashed curve here. But again, what was the kind of selling point? If you really worry about dissipative effects, maybe the dissipative protocol will do better. So if I now look at the one-axis twist protocol, twist, untwist, also include single spin cooperativity, either to dephasing or to relaxation, then you're actually orders of magnitude worse. Okay, so the upshot is this is a different way of mimicking the nice physics of that twist-untwist protocol in a dissipative way. This dissipative protocol has more robustness against single spin dissipation. Okay, and I'm pretty much out of time. I will just flash a slide indicating that there are ways of doing this experimentally. If there are questions, I can maybe say more about that. This is something that Anya's group is working towards with NV centers in a diamond optomechanical crystal. And I do not want to make Klaus angry, so I'm going to flash to the conclusions. And yeah, thank you for your time.
Thank you very much. Perhaps you planted a few questions in the audience, so let's see how that worked. Anna-Maria?
Yes, very, very nice talk, Ash. So I have a very basic question that maybe a detail that I'm not understanding. So you're saying there is a G, when you have at the beginning the equation for the amplification,
Yep.
You put it in the numerator and the denominator, but we know that in the ideal case, the noise goes back to in quarters, but the signal is amplified. Yes, so in your...
Yes, maybe I should go back to the very...
Yeah, when you have the...
Let's go back even further just to
yeah.
really make it, yeah, and that's why I tried to... Let's go back to here,
This,
right?
yes, I'm
so,
not
so
only...
here, so this is the signal being amplified.
Yes, but why you put, I mean, but the noise, why you amplify the variance goes back to n quarters, yes? I mean, you are...
So this is just the gain process, right? So when I introduce this, so imagine you just use one-axis twist to basically, you pick the sign wrong, to just amplify. So the idea is that if you're really doing the whole thing, you already squeeze this. So if you want, this would already have a 1 over G squared.
Okay,
yeah.
I understand.
So this is just the half. This is the untwist.
Okay, sorry, I missed that. Yeah. Okay.
Thank you for the talk. Curiosity, can you say something about that strange even odd effect and that value at which there is this, is it a drastic change or is it just the way
and I should point out that Diego in Ana Maria's group has a really nice paper that also provides intuition of this. I have okay, bear with me, there is a slide on this because this question comes up a lot. Can we find the slide? Maybe not. Oh, here we go. Okay, so this is my my condensed matter way of thinking about, you know, a spin squeeze state. I like to think of it like a superconductor, right? So a spin
kind
squeeze,
of a blockade that
it's a spin squeeze state, right? Has pairing correlations in it, right? And now there's a problem having perfect pairing correlations depending on how many levels I have, right? So the spin squeeze state, it needs to be annihilated by this combination of a lowering and a raising operator. How do I do that? I need a superposition of just 0 excitations, 2, 4, 6, 8. Okay, so if I have an even, you know, number of spins, I can get destructive interference for all these transitions to the odd levels. I can't do that when I have odd. And that's something that is a problem no matter how big n is.
Thank you.
I saw here.
So I have two questions. One is that is your spin squeezing scheme unitary? The second one is that you assume that when you were doing this amplification, the noise somehow stayed constant, but often this is hard experimentally when you amplify something, noise often gets amplified too.
So the first thing is like we're using non-unitary evolution, right? So this initial squeeze step and this amplification step, we're really using dissipation that we've kind of introduced deliberately on the spin ensemble from this funny cavity that we've played tricks on. So it is not a fully unitary process, and that's by design, right?
So you will have a lot of anti-squeezing then.
What's that, sorry?
You will have actual anti-squeezing.
So this second process here, right, is actually generating. It's an amplification process. But at the end of the day, these things all together conspire to giving you an estimation error that's lower than the standard quantum limit, right? So at the end of the day, like going back to Anne-Maria's picture, you're basically back to having noise that is pretty much at the projection noise limit, but you've made the signal much, much bigger, and your amplifier has not added any noise, right? So whether I squeeze and keep the signal the same, or whether I don't squeeze and I noiselessly amplify, in terms of my estimation error, those are equivalent.
Yeah, but in terms of using this squeeze state for measuring something,
but that's what this is. This is the estimation error. So it is like, that's the thing I want to use it for. Yeah.
But if you have this ununitary process, you will have more anti-squeezing, and there are papers showing, for example, a paper from Braden's group, theoretical paper by Boris Braverman.
So this is a very different, I think, protocol than like things considered in those papers. And I will point out, in the perfect case, that's what this is showing. You know, this is basically like your inverse metrological gain. In the perfect case, that's this green dash curve. You're doing worse than this completely unitary protocol, which is twist untwist, one axis twisting. But then the point I tried to make is, as soon as you introduce some extra single spin dissipation, this dissipative scheme I've introduced does better. Well, that's another issue.
I think we will maybe defer.
I'm happy to discuss more too. Yeah.
And let's take another question.
Okay.
Thanks, Ash. That was a great talk. Is there a way to use the bosonic analog to understand how your amplification doesn't actually degrade your SNR for like large N? Because it's very counterintuitive to me that it's not dependent on N.
So in the bosonic case, if you want N is infinity, right? Because N is like your local Hilbert space dimension. Right. And so in the bosonic case, life is really easy. Like that's what this was supposed to be indicating. You could, in principle, amplify forever, right? So that exponential growth rate will give me a factor e to the gamma t. That could be arbitrarily large. And in principle, you can't stop me from making that R parameter as big as I want to. So in the bosonic case, you can really have your cake and eat it too. You can have lots and lots of gain, lots of squeezing. You're using the fact that in this perfect linear oscillator, you have an unbounded Hilbert space dimension. The fact that there's constraints in the spin problem having to do with N, that is really unique to the spin problem. There's no N in the single bosonic mode. You can definitely talk more about that.
Yeah, okay. Yeah, maybe I'm not phrasing my question right.
So this superradiant amplification approach, you need the radiative decay rate to be the dominant process. Is that natural for these solid-state spin systems, or is that kind of hard to achieve? Is it the collective radiative decay? Do you get an enhancement along those lines?
So the thing that this is trying to show is that it is the, so this, and I should have defined these cooperativities, right? So this eta parameter here is really a measure of how good is the good interaction with this funny cavity mode that's doing interesting things compared to the intrinsic T1 decay time of your spins, right? And so the situation is what you're describing. The relevant parameter is not the size of this. Here, that's order 1, and things are still working really well. The relevant parameter is basically that times N. So there is a collective enhancement here that gives you some insensitivity to those single spin dissipative effects. The same thing is true for single spin dephasing.
Thanks, Ash. So I like this idea. I think about it like a pencil on a table. You encode the phase into the slight tilt of the pencil, and you see which way the pencil falls. You say, "Ha, that's the way I initially did it." You correctly point out that's a nonlinear process, And these results you have about amplification apply for linear amplifiers, Ks et al. And so on, this half photon added. And so my question is, I'm wondering if you did something maybe even more clever, can you get around these half photon added noise by using this somehow nonlinear process?
Yeah, so the first thing I want to make it clear is this was just supposed to be an analogy and to give me some expectation. I did not do some magic and say my spin system are bosons and let's hope for the best. It's just an analogy. And I guess one of the questions is, yeah, I don't even think we know how to really rigorously prove that in this, this is not even like the squeeze superradiant decay. Like in general, can one prove that that added noise is really bounded by one? Could you do better? Well, on some level, the squeeze superradiant version of this does do better. So if you want this process here, it's amplifying both Sx and Sy, right? So if I start away from the North Pole in any direction, it's going to get amplified. The second thing I told you about with the more complicated dissipator, then I got to really tilt in the Y direction. If I tilt in the X direction, I'm going to actually de-amplify that. And so that process does give you, that's why the whole thing works, less added noise. Yeah.
So a couple of questions. So how certain can experimentalists be that they have 200 spins and not 201 or 199?
So the cop-out is I'm not an experimentalist, so you'd have to ask them. But,
the
more relevant answer is this, right? So the relevant answer is, okay, to really see this effect, this is in dB, right? So you would need to sort of engineer this dissipator with an enormous, enormous R parameter, right? The size of the dynamics is kind of growing. So if you don't want this to mess up your experiment, just work out here. Look, you're almost at the Heisenberg level of squeezing, and now there's no even odd effect. So I would almost say the harder thing would be to actually be in a regime where for a large ensemble, you could actually realize this dynamics and see that effect. I think for most experiments, the ways that you would realize this, you'd be out here somewhere, you couldn't tell the difference. Yeah.
And a second question, where did that 1.3 come from?
I'm asking you, right? So that's, we've done that through exact master equation simulations. Mean field theory gives something consistent. We don't have any fundamental understanding of where it comes from. Is it a fundamental limit? Could you do better, right? It's, yeah. There's been some interesting work, for example, on nonlinear quantum amplifiers, I think from Josh Combs. Like we talked to him a little bit about, could we use that to understand this a bit?
Right, Diego.
Just very quick. For large R, would you expect like all these dynamics to be slower? Because for large R, it becomes more like Sx or Sy, for example.
You mean the generation of the squeezing and stuff? Yeah, so it depends how you scale things. So if I keep the gamma fixed, then no, it's still okay. But the problem is, what's the size of this dissipator, right? What are the size of the interactions I need to generate? It's not just gamma, there's an e to the 2r there, right? So if I actually keep the product of gamma e to the 2r fixed, which is the experimentally more relevant thing, then absolutely there's a slowdown going on, right? And again, when we do the simulations of the full protocol where we try to sort of include the effects of single spin dissipation, we try to account for these effects in an honest way. So that's going into the price you pay, right? When you have something that tells you can't take forever, right? There's single spin dissipation that will kill you if you take too long.
Super. Any last question? Maybe just one comment. If you go to the extreme right of that figure and you have the very squeezed case of 200 spins, you lose just one. You will of course jump up to the high value because that single spin going away will have a variance of a quarter, and therefore the remaining 199.
So you clearly were not the referee of our paper, because I think
I'm not the referee of your paper.
So we wrote this. We said, oh, this might be, and I thought we were very gentle. This might be a really interesting sensing modality, and there was a referee who really did not like this. So the published version, but I still think it's an interest. it's kind of a crazy effect. Okay, it's a really difficult regime to be in, but could you exploit that for something like?
I mean, what I'm thinking is that that very squeeze state is like an SX eigenstate around S equal to 0. And of course, for the odd spin, that doesn't exist because it's half integer.
Exactly.
And there's a degeneracy between the two. And that's
Yeah.
probably what gives that upper curve, right?
Yeah.
That you have an even
I think
mixture.
it's another way of just understanding that argument I had.
So why don't you then just break the symmetry and pick the SX equal to +1 half eigenstate, which could be super squeezed also?
So why doesn't the dynamics do that?
I know why your dynamics doesn't, but could you just add a little bit of asymmetry that would bias it and then go to that one? So then it would work for odd and
but again,
even.
I think that the easier experimental solution is like sacrifice that factor of 2.
Okay. I thought we were ambitious here, actually.
Yeah, sorry.
Super. Okay, any more questions? Okay, last question. Manke?
Seeing superradiance in the solar system, because I'm ignorant about this. So there are definitely like many experiments that have probed superradiance, but not in the context, this kind of sensing context. Let me just use this as an excuse to show you the one slide on Anya's experiments, right? So the approach that we're pursuing, again, in the spirit of being ambitious, is to actually have the bosonic mode of interest not be a photonic mode at all, but use a phononic mode. So this is an optomechanical crystal. There's a localized phonon mode sitting around where these NV centers are. We're actually even thinking about, or Anya is thinking about using these SIV defects that have a large strain coupling, right, to this mechanical motion. This is the system where we think the numbers look promising enough to see this superradiant decay, right? So, and this is also, these are the spins that we actually want to, to measure and amplify. They haven't seen a superradiant. No. Absolutely not, yeah.
Great. And with that, let's thank Aashish again.